Alright, so in the last video we looked at control of the cardiac cycle, and in this video we'll look at regulation. And while the nervous system is not required to make the heart beat, there is a lot of control that's exerted by the nervous system on the function of the heart. And so we're going to go there next. Alright, so if you recall from last semester, autonomic nervous system controls much of the organ function of the body, and there are two types or two divisions within the autonomic nervous system: the parasympathetic division and the sympathetic division. So take a moment and think about which of these is fight or flight. You may want to pause the video for a second and think about that, and then come back to me. Okay, so hopefully you've done a little bit of thinking. So sympathetic division, is that fight or flight or rest and digest? That's the fight or flight. So sympathetic is what gets the body ramped up for action. Parasympathetic stimulation is what slows you down. That's rest and digest. Calms you so that you and brings the body into maintenance work. So we'll start with parasympathetic innervation. It's provided by a branch off the vagus nerve. If you recall, the vagus nerve is one of the cranial nerves, and it's the one that goes farthest afield. It's the wanderer. The neurotransmitter that's used by the vagus system is acetylcholine, and there is constant low-level innervation, innervation isn't the right word, but constant low-level stimulation coming from the parasympathetic division that is constantly slowing the rate of the heart. It acts both at the SA and the AV node, and as stimulation by the vagus nerve with acetylcholine is provided, it slows the heart rate down. So you slow the heart rate with acetylcholine. And we have this constant low-level brake. You can almost think of it as like driving around town in your car with the brake slightly depressed. And so it keeps the heart rate just a little bit slower than what it normally would be if there was none. And so one way that you can speed up the heart is by decreasing parasympathetic stimulation. I'll give you a chance to think about that for a second. If you're always riding around town with your foot on the brake, you're going to be going a little bit slower. And so one way to speed up is to take your foot off the brake, and your car will just naturally go a little faster. And it's the same with your heart. So you can speed up the heart just a little bit by slowing the amount of parasympathetic stimulation you give. There's also sympathetic innervation to the heart at the SA and the AV nodes, and it's provided by a set of nerves that are referred to as the accelerator nerves. They use norepinephrine as their neurotransmitter, and if you stimulate these nerves, these accelerator nerves, then they're going to release norepinephrine, and what we see is an increase in heart rate. So two ways to speed up the heart: either by decreasing parasympathetic stimulation that's always going, or by increasing sympathetic stimulation. It's all reflexive, this regulation, and it's provided by the cardiac center. The cardiac center is found in the medulla oblongata. And they respond reflexively to information that's being provided about blood pressure. There are two centers in the medulla oblongata that control the heart. There's the cardio inhibitor reflex center, and when it fires out stimulation, then it's going to slow down the heart rate and force. So it sends signals along the parasympathetic pathways. The cardioaccelerator reflex center increases heart rate and force by sending out stimulatory signals via the accelerator nerves and sending out norepinephrine, releasing norepinephrine. So these reflexes are initiated by baroreceptors. So think for a minute, what are the baroreceptors? Barometer is in the word. So baro is about sensing pressure. So baroreceptors are found in the aortic arch, in the carotid arteries, and in the plural for vena cava is veni cavi. They sense changes in the blood pressure. In response to an increase in blood pressure, what we see is stretching of the baroreceptor that sends a signal up to the cardioinhibitor reflex center. We get parasympathetic stimulation that slows the heart rate. That means that less blood is being pushed from the heart. And as a result of this parasympathetic stimulation, we see a decrease in blood pressure. So increased blood pressure triggers a decrease in blood pressure through the cardioinhibitor reflex center. Increase in blood pressure at the vena cava now. Oh, and by the way, this is increases in blood pressure at the aorta and the carotid arteries. Should have mentioned that in my notes. On the other hand, if we see increase in blood pressure at the vena cava or at the right atrium, where the vena cava, where the superior vena cava and the inferior vena cava come in, if we see increase in blood pressure there, that means that there's more blood coming into the heart than the blood is ready to move on out. And so what we need to do as a result of increased blood pressure on the venous side of the heart is increase the rate of the heart so that we can move that blood that's coming into the heart, move it right on through the heart. And so we see, as a result of that, stretching of those baroreceptors, we see a reflex that is moderated by the cardioaccelerator reflex center that speeds up the heart rate by sending out transmission along the sympathetic pathways. And as the heart speeds up, more blood is moved out of the vena cava. We see decreased blood pressure there, and everything returns to homeostasis. Okay, so baroreceptor reflexes are what manage the blood pressure in both the arterial and venous sides of the heart. There are other ways that we regulate the cardiac function. Strong emotions and distress can lead to stimulation of the autonomic nervous system. So if you're really scared, or if you are threatened in some way, or if you're experiencing really happy emotions of love or joy, you can see cardioacceleration as a result of that. Body temperature can also cause changes in cardiac cycle, in the regulation there. So if you get a fever, frequently you see increased heart rate. A decrease in temperature slows the heart rate. Ion concentrations in body fluids will also affect the production of action potentials and of heart rate. So hyperkalemia, that means high potassium in the blood, will cause a decreased heart rate and force. Hypokalemia, that should say low, sorry about that. Low potassium will cause arrhythmias. Try that again so that you can actually read it. There we go. Low is hypokalemia. Hypercalcemia, that means high calcium in the blood, will increase heart rate and force, while hypocalcemia will cause decrease in heart rate and force. So just some of the other controls that may be involved in regulation of the cardiac cycle. And finally, some clinical issues associated with heart rate and heartbeat. Bradycardia, that's a slow heart rate, something less than 60 beats per minute. That can be very adaptive, so frequently athletes will show bradycardia because their hearts are so strong, the force with which they pump is sufficient to oxygenate the blood, even though they have fewer heart beats per minute. Tachycardia, that's rapid heart rate, so sustained rapid heart rate, even when you're not exerting yourself, is referred to as tachycardia. Think of the tachometer in your car that's telling you how rapidly the engine is turning. So tachy means fast, brady means slow. Fibrillation, that's a hard one to say sometimes, that occurs as different portions of the myocardia cause that they contract in uncoordinated chaotic tempo. And so this is when the muscle cells themselves, little clusters of them will contract inappropriately, and that results in really chaotic, very uncoordinated contractions of the heart. So atrial fibrillation is not uncommon, especially in older folk, and it can be problematic because it will interfere with appropriate blood flow. People with atrial fibrillation frequently have reduced energy because they're not getting sufficient oxygen. It can also lead to bizarre, pooling of the blood, especially around valves, and result in the production of blood clots that can then become circulating emboli, and that's a bad thing. And then there are a lot of other issues that are found in the book in one of the boxes on between pages 574 and 575. So be sure to check that out. Okay, so there we've talked about a lot of the regulation of the cardiac cycle, and I'll see you in the next video.